Good evening and welcome to today's lecture on alternative fuels and sustainability. Last week we had seen a short introduction to alternative fuels, and today we'll be seeing more in depth on the sustainability of alternative fuels and comparison between them and so on, right? So here are the contents for today's lecture. First, we'll have the discussion of last week's answers, like the answers to last week questions, and then we'll go for a quick recap of about the need for biofuels and the policy measures taken by the Indian government. Then we will look at the sustainability measurement of biofuel pathways. Okay, so what are the indicators, criteria, the dimensions that you need to consider? All right, and then there will be I'll just tell you about a short case study, about ethanol production in Maharashtra, and then we'll go into the questions for this week. And finally, if time permits, we'll just do a short activity, or what you can do is you can just take a screenshot of it and then do it at home, even that's fine. So the answers to last week questions. First, what does the 8.5 in RCP 8.5 stand for? So RCP is representative concentration pathway. So these are pathways for primary energy use to achieve certain radiative forcing. Okay, so what is radiative forcing? It is the amount of energy in the amount of energy dissipated to the atmosphere, because of which the temperature rises essentially. So, and it is taken from the start of the industrial revolution. So from the year 1750 AD until now. In this study, up to they've taken up to the year 2100. Okay, and so this 8.5 stands for radiative forcing, and it is measured in watt per meter squared. All right. So second question was, which of the following statements are true? So as we had discussed last week, the first generation biofuels are produced from food grains. Second generation biofuels they are also known as advanced biofuels, and they are produced from agricultural residues that are residues that is a byproduct of agriculture, right? So you have the main crop, and then you have the residues like rice straw, wheat straw, and so on, and they are not edible, of course, so non-food biomass. So all the three statements are true, so your answer is D, all of the above. The third question was, which among these biomass to biofuel conversion pathways come under the thermochemical conversion? So as you can see here, see your options of fermentation. Fermentation is a biochemical process that is used to obtain ethanol. All right. Anaerobic digestion is again a biochemical process, and that is it's a process to generate biogas or methane. All right. And pyrolysis is the process where you heat biomass or heat organic content in the absence of air. Okay, so what happens is that is so you produce bio oils using this pyrolysis. You can also produce charcoals. Okay, charcoal is produced using it's a product of pyrolysis. Okay, so pyrolysis is a thermochemical process. Number 4, there was some confusion with regards to differential pricing last week when I had discussed it. So I'll just make it a little more clear. You can see this table here. I wanted to discuss this last week, but I had forgotten to include it in the slides. So what is differential pricing? So essentially, to enhance the ethanol industry in India, what the government has done is that they have introduced certain measures. The first measure was like the use of multiple feedstocks. Then there is the differential pricing. So differential pricing is basically you have different feedstocks to produce ethanol. Okay, like B heavy, C heavy molasses, sugar syrup, damaged food grains, or maize, and surplus rice from the Food Corporation of India. So the difference between B heavy and C heavy molasses is just they're byproducts of the sugar industry. They are obtained at different stages of sugar of the refining process, and normally C heavy molasses has higher have higher sugar content, and it's easy to convert them into ethanol. So this costs less, like the cost of this converting C heavy molasses into ethanol is lower than that of B heavy molasses. So based on the feedstock used, the government said that okay, we will procure it at different rates based on the costs that you incur. So that is known as differential pricing policy. All right. And the option B, reimbursing the ethanol production companies a part of the capital cost of the ethanol plants. This is called viability gap funding. Okay, this is also part of policy for second generation ethanol. For first generation, not so much. The next question, why is biomass considered a carbon neutral source of energy? So biomass is basically recently living organic matter derived mostly from plants. There is animal matter also, but it's mostly plants. So plants absorb carbon dioxide and release oxygen through photosynthesis. All right. So the CO2 that they have absorbed is the same amount of CO2 that is released when you combust biomass. All right. So because of this, there is no new CO2 that is being added to the atmosphere. So we consider this as carbon neutral. All right. Number 6 is electric vehicles have no tailpipe emissions, but they also contribute to greenhouse gas emissions. So how do they do that? So there are two things here. First is manufacturing of the electric vehicle components. Of course, it requires a lot of it requires electricity as well as other resources, and so indirectly the manufacturing process also emits CO2. But if you see during the charging, since we are using the grid power for charging, we don't have any solar modules for charging yet. 80% of the total electricity was generated from coal. Okay, in the month of February 2020. Okay, and sorry, this is from thermal power plants that includes coal, natural gas, and oil. Okay, and renewable energy is about 10%, hydro 7%, and nuclear is 3%. Okay, all three are non-polluting, as in they don't emit any greenhouse gases, but 80% comes from coal. So that is the reason why I mean it's an indirect emission, right, even though there are no tailpipe emissions. So your answer is both A and B. Okay. So question 7, why is the sustainability of first generation bioethanol under debate despite its potential to reduce the need for fossil fuels? So initially when you consider the environmental aspect of it, when you flood the fields, right, agricultural fields, especially when you are cultivating during the cultivation of rice, it creates anaerobic conditions for the methanogenic bacteria or microorganisms to produce methane. And overall, globally, 20% of the methanol emissions come from agriculture. Okay, And there are also nitrous oxide emissions that arise from the use of nitrogenous fertilizers like urea and all that. And these are the environmental reasons. And then we come to the social aspect of it. So diverting food grains and crops towards ethanol production, there will be a shortage. There could be a shortage of food, like for instance, in India, the Food Corporation of India has allowed ethanol plants to use their surplus rice and surplus grains for ethanol production. These are perfectly good grains. Okay, so if that happens in the future, if we require those grains, then it will be a problem. Then we have to choose between the two, right? Are we going to eradicate hunger, or are we going to produce ethanol? Okay, so that's a conflicting objective right there. Okay, and then the next point is, when we move towards higher blends of ethanol, what happens is the engine and the components inside the vehicles need to be changed. They have to be designed and calibrated to handle the high amounts of ethanol. Okay, and about 10 years back, 10 to 12 years back, in Sweden, there was an issue of high sulfur content in ethanol. Okay, although we have standards now that restrict the sulfur content and any corrosive content, the issue was that it actually corroded the insides of the vehicles that they used. So because of that, there has been a general aversion towards ethanol since then, all right, in Sweden. Although now those problems are solved, okay, but there is that kind of doubt in their minds, right? So the answer to this question is all of the above. So all these three statements are right, okay, when it comes to sustainability, when we debate the sustainability of first generation ethanol. The next question was short numerical, right? A small numerical here. So the 20% blend in bioethanol, okay. So the estimated consumption of petrol in the year 2025 is 3.5 crore tons. So calculate the amount of ethanol needed to be produced in 2025 to satisfy this demand. So you can take a density of petrol as 800 kg per meter cube. So the hint is use the density formula, and there are some conversions here. So how do you solve this? First, you have the amount of petrol in crore tons. You just convert it into kg. So multiply by 10 power 7 and 1000 kg per ton. You get it in kg. Then you convert this into liters by using the density formula, right? So you have so many kgs, you divide it by the density, you get it in meter cube, and 1000 liter per meter cube will give you the liters, right? Yeah, so amount of petrol in liters. 20% of that is your ethanol. So 20% of that, it will give you 875 crore liters. So we are at the end of the previous week's answers. Now let us come to today's lecture, right? So a short recap: why do we need biofuels, or how can biofuels help? Like let's see this pie chart here. I've shown this to you already last week, if you can recall, right? So the fuel consumption, all right, accounts for 65%, nearly 2/3 of all emissions, all the life cycle greenhouse gas emissions for vehicles in India. All right, so that's almost 2/3, right? So when we go for biofuels, what will happen is, as biofuels are considered carbon neutral, the tailpipe emissions, whatever tailpipe emissions of carbon dioxide are there, right? They are all carbon neutral, so there is no new addition of carbon dioxide in the atmosphere. So this value will come down, not the percentage, I mean the absolute value of the emissions during fuel consumption will come down. Although there will be some emissions during the fuel production and manufacture and maintenance, there is a huge opportunity here if we use biofuels. Okay. And then a quick recap on the policy efforts in India. As you can see, since 2003 onwards, there have been ethanol and biodiesel policies. Okay. So in 2003, the target was 5% ethanol in petrol. Today, we have 20% as our target by 2025. Okay. But over the years, the issue has been that the lack of availability of feedstock has kind of stalled the entire ethanol program. So, in the past few years, the government has addressed certain bottlenecks, like I just told you last week, right? And yeah, so because of that, we are at 10% right now, and we are well on track to achieve 20% by 2025. Okay, and you can also see biodiesel here. Target of 20% was envisaged in 2003 itself, on 2003 to 5, around that time. But now in 2018, the national policy on biofuel envisages only 5% by 2030. Okay, so you see there is a huge drop here. That is because here the feedstock that people thought they will be using was jatropha. There is a crop called jatropha that you can plant. Okay, and the seed of the jatropha plant contains oil. Okay, you can convert that into biodiesel. But now what they are doing is they are going in for used cooking oil. So the cooking oil that you use in your kitchen, they can use that, they can use that to convert that into biodiesel. Basically, there is a process called transesterification. So through that process, they can convert it into biodiesel. Okay. So they are doing that with restaurants and big hotels and stuff. Okay, they're not doing domestic yet, because domestic, of course, it is too much scattered to get the used cooking oil, right? Okay. So how do we know if biofuels are sustainable or not? So basically, you need some dimensions, criteria, indicators, composite indicators. It is the same procedure as I had told you in the first week, right? I told you about how sustainability was measured for cities. It's the same procedure. Okay, except only the parameters will change, only the criteria will change. That's it. So you have 3 dimensions. So techno-economic, so environmental and social. So normally technical and economic are clubbed together. All right. So in technical criteria, you have something called net energy ratio. So what is this net energy ratio? It is very similar to the energy efficiency, but this is a ratio of the output, total energy output that you get, to the fossil energy input. So only the fossil energy input is considered. So if the net energy ratio is more than 1, okay, you know that the energy efficiency can never be more than 1, because it's a percentage, and you know the second law of thermodynamics and all that. But net energy ratio considers only the fossil energy input. So your project is really good, or your system is really good, if your net energy ratio is more than 1. Okay, and technology maturity level, technology maturity is measured in something called TRL, technology release level. So that's a level like from 1 to 10, and about 7 or 8 is like that the technology has come into the market and it is now commercial, and it's commercially viable. So that's what it means. And then you have biofuel yield, that is kg of or liters of biofuel per kg of biomass, and so on. And then you have in the economic criteria, of course, you have the production cost and levelized cost, then capital cost, operation and maintenance. One second, I'll just show you. So production costs, levelized cost, capital cost, operation and maintenance, and then you have the transportation cost. And this is a very important indicator, feedstock availability. Okay, feedstock has to be available for you to produce biofuel, right? So that is very important. And then of course you have net present value, internal rate of return, and so on. So in the environmental criteria, you have global warming potential, acidification, eutrophication, human toxicity, land footprint, and water footprint. Okay, and social, you have social acceptance. This is a very subjective indicator. It's some of the studies have tried to quantify it, but it's still very qualitative indicator. All right, health and safety risk, it's measured in number of accidents, or maybe even the health expenditure, like how much money is spent on health, on healthcare, and so on. Job creation, there is number of jobs created, and so on, right? So some concepts, so these are economic concepts: time value of money, levelized cost, economies of scale. So I'll start off with the time value of money. So consider that you have 100 rupees in your hand today. Okay, so you invest it, let's say you invest it in FD, and that bank is giving you 5% interest wherever you have invested, right? So that means that next year at this time you will have 105 rupees in hand. So that 5 rupees is something that you have earned, that your money has earned 5 rupees. Okay, but if you have given that money to someone, or if you have to receive that money from that person, and instead of giving it today, that person tells you that they will give it to you 1 year later. Okay, but it will be the same 100 rupees. It's not earning any money. So instead of investing it today, you will be investing it 1 year later. That means you are at a loss of 5 rupees. That 5% which you could have learned, which you could have earned, right, is a loss right now, because that person has said, that person says that he will give it to you next year. Okay, so that is basically the time value of money. So it is also to be considered not just for your investment, but also for like some loans you may take for any project. You will have an equity and a debt part. So equity is what you invest, and debt is what you take from the bank, and you will have to pay some interest rate to the bank. Okay, so the effective discount rate is what is used to calculate the future and present value. So there is a simple formula. You remember the compounding formula. It's very similar to that. So the future value is measured as the present value times the times 1 plus the effective interest rate, the whole to the power of the number of years, or number the time period that you are considering. So with this you can calculate the future value of your investment today. So if you have an investment of, let's say, 100 rupees, and you want to calculate after 10 years what will be the value of this investment, you can calculate using this formula. Next is the levelized cost. So see, each year there will be some changes in the costs, right? You won't be paying the same amount of money to your, let's say, to your employees, or you won't be spending the same amount of money for equipment and for fuel and all that. Okay, because there is inflation. Okay, or there is some escalation due to some local and global factors. Okay, the crude oil, for instance, if you are using diesel in your system for some reason, and the diesel cost is like unpredictable. It could increase, it could decrease. So that is escalation. and in the economy you have inflation. Okay, so you need to consider all of that, and you also need to consider the time value of money. Okay, so because of all this, your cash flows are not the same, are not equal for each year. All right, it will be different. So you need a representative value to say how good your project is, okay, economically. So that representative value is the levelized cost. That means it, as the name suggests, it will equalize your uh, uh, different cash flows and then give you, okay, if I take, let's say, the whole lifetime of the project is like 25 years. Over the lifetime, each year you're spending this much. Okay, I take all that and then I equalize it to something called annuities. Annuities are like equal amounts of money paid in each year. Okay, at the end of each year. So that will give you a very good idea about how good your project is, and it's a kind of standardization to evaluate and compare projects with different lifetimes and capacities. Okay. So third is economies of scale. So think about it in this way. So when you buy something in bulk, right? Let's say wholesale. You go and buy 1000 kgs of rice from the market, right? APMC or wherever it is, and you as a customer buy for your house 5 kgs of rice from the retailer, from the shop. So who do you think will get it for a lower rate? So obviously the retailer will get it from the wholesaler for a lower rate than what you will get it than what you will get the rice for from the retailer, right? So that is basically the economies of scale. Because of the quantity, in this case it is quantity, but when it comes to engineering problems, to big systems and such, you can consider the volume or the capacity. So when you have larger capacities, naturally it will cost lesser, like the unit rate will be lesser. Okay, so generally it is given by this formula, C1 by C2 equals V1 by V2 whole to the power alpha. So C1 is the cost of C1 and C2 are costs, V1 and V2 are the volumes or the capacities or whatever, and alpha here is the scaling factor. All right. So the scaling factor can be obtained through literature or through vendor quotations or whatever it is. Okay, and or a good thumb rule is you can consider this as 0.6. That is a very good approximation, and it is also given in literature why that 0.6 could be a very good approximation, right? So if you want to know further on how to carry out economic analysis of projects and such, you can read this book called Thermal Design and Optimization. They have excellent definitions, and they've explained the concepts really well about all these about economic analysis basically. All right. Next, the environmental concepts, environmental indicators, the global warming potential. So as I told you earlier, methane and nitrous oxide are also greenhouse gases, and they are more potent than carbon dioxide. Okay, so global warming potential is the cumulative radiative forcing resulting from the emission of greenhouse gases. Okay, and it is measured in kg of CO2 equivalent. So for methane it is 25 times of CO2, and for nitrous oxide it's about 300 times. So you just add up all that and you'll get the global warming potential. So normally it is measured for 20 years or 100 years. Next is acidification. So what is acidification? It is it is an environmental indicator that measures the amount of gases responsible for acidification of soil, water, ecosystems, and the building environment. It is measured in kilogram of sulfur dioxide equivalent. So normally, because of nitrogen fertilizers, you have ammonia and NOx emissions from the fields. They can cause acidification. So eutrophication. What is eutrophication? So you apply these fertilizers, but the entire fertilizer is not taken up by the plant, right? So whatever is excess, it goes as a runoff to water bodies and into the seepage into the soil. So because of these excess nutrients, availability of these excess nutrients, there will be algae growth in these places, in water bodies and such, and that will take up all the oxygen, dissolved oxygen within the water body, and less oxygen will be available for the creatures living within the water bodies itself. Okay, so that will cause depletion of marine ecosystems and so on. So that is eutrophication. Okay, and it is measured in kg phosphate equivalent. So next, how do you what is the methodology that you can use? I think you would have learned already about life cycle assessment. So this is life cycle sustainability assessment, which is a combination of life cycle costing, environmental and social life cycle assessment. So there are four steps to do this. The first is goal and scope definition, where you define the functional unit. That is, it could be per liter or per kg of biofuel or something like that. And then you define the system boundaries. Okay, I'll come to this in a moment. Second is preparation of inventory, that is inputs and outputs of the entire system. Then the impact assessment. So you convert this into categories, and then use the inventory parameters. You can convert them into categories, and then you can quantify the impacts. And then the fourth is interpretation, that is generation of a set of conclusions and recommendations. So when we talk about system boundaries, right? So I think last week we would have had a lecture about the LCA of a product itself, the life cycle of a product. Here we are talking about the process, right? So let's say that we are producing biofuel here. Okay, so there are many different processes that go into this, right, producing biofuels. So you set your system boundaries. So let's say I'm starting from the agricultural field. Okay, so that's my starting point. Then I have various different plants and various different inputs and outputs that go into different plants, and then finally I have this biofuel conversion plant, and I have my biofuel output. So I set my functional unit, and I say I divide it into many different processes or plants, and then I analyze the input and output for each plant. Okay, so that's how basically this is being done. Okay, that's how it is done for a process. Okay, so then one of the most important indicators to measure biofuel sustainability is the feedstock transportation. Okay, so why is it very important? Now let's see here. The feedstock transportation cost is dependent directly on the distance traveled. Okay, so and it is inversely dependent on the carrying capacity of the vehicle, that is the weight carrying capacity of the vehicle. So let's say you have some vehicle, right, and the volume of the vehicle is fixed. Okay, so if the volume is fixed, there is something called bulk density. Okay, what is bulk density? It is when you take a bulk, like the name suggests, a bulk of the biomass, and then you put it in a huge container like this vehicle, like the truck or something. The the volume that this weight of this biomass occupies is called bulk density. Okay, so if there is loose biomass, then there is a lot of white space in between. Okay, it is not compressed or it is not densified. Okay, so if you just take loose loose let's say rice straw or something and then put it into a truck, you're not going to be able to transport a lot. Okay, so but if you pelletize it or if you densify it, like you can see here, pelletization or briquetting, if you do, then that will increase the density of the biomass. Okay, the bulk density increases, and because of that you will be able to transport that biomass, the densified biomass, in fewer trips basically. Okay, so that's why bulk density is a very crucial in deciding the transportation cost. All right. So because the transportation cost is dependent on the distance, when you're designing a system for, or when you're designing a supply chain for biofuel, you need to decide on the radius, that is the radius of procurement of your biomass. Okay, you can't say that, okay, I have a plant here, I'll procure my biomass from 700 kilometers away, because that's going to increase your transportation cost. Okay, but you can't also say that I'm procuring it from only 20 kilometers away, because you need to have the availability of biomass in that area, right? So you have to design the system in such a way that there is enough biomass available, and also you minimize the cost of transportation. But there is a conflicting objective here, because if the capacity of your plant is higher, due to economies of scale, your cost will be lower, the capital cost. But then if you do that, then your transportation cost will increase. So there should be a trade-off between the transportation cost and your capital cost in this case. All right. So we come to the case study of this ethanol production in Maharashtra. So this study has optimized ethanol production based on regional resource availability. Okay, and it evaluates potential for ethanol production in 33 districts of Maharashtra, and there are some constraints. I'll come to that shortly. Sorry. So the study considers 4 objectives. Okay, so this is a multi-objective optimization. I'll explain you what that is. So increasing farmers' income, reducing ethanol costs, reducing water footprint, and reducing irrigation water utilization. Now, if you see, look at the first 2 objectives, increasing farmers' income and reducing ethanol costs. They are conflicting, because if you offer them more price for their biomass, then naturally you're increasing their income, right? But if you do that, you're also increasing the price of your cost of ethanol, okay, because you've just paid more to procure biomass. So there is these 2 are conflicting objectives, and there needs to be some trade-off between the 2. So this study uses like a Pareto optimization. I'm not going into the details of what a Pareto optimization is. Okay, so this is basically to forge a trade-off between conflicting objectives. So sorghum, wheat, and cotton are the most recommended crops for ethanol production, and these 3 are the districts. Jalna, Kolhapur, and Pune are the most selected locations. All right. So this is what the study has done. So this is the optimization model with the 4 objectives. So the parameters that are that they have considered are crop water requirement, crop and residue yield, ethanol yield, and cost of farming. And these are the constraints. Okay, the land availability is a constraint. Okay, then you have ethanol demand, and then the water availability, that is also another constraint. So and these are your outputs. So how much groundwater recharge is happening, so this goes into these constraints as well, because if more groundwater is available, you will require lesser irrigation water, right? Yeah. So then these two are there are another two outputs, district wise crop allocation and biorefinery design. So these are some of the numbers based on the optimization of each parameter. So you have minimization of let's take this for example, minimization of ethanol cost. So if you do this, if you consider this as your objective, then obviously the cost of ethanol is going to be lower than if you had considered any of the other three objectives. Okay, so this is the lowest among the four, right? So similarly, if you consider farmers profit, if you want to if this is your sole objective, then obviously you can see that the farmers profit is huge in this case compared to if we had considered any of the three other objectives, right? So but like I said, these two are like conflicting objectives, and you have to use that Pareto optimization to arrive at, let's say, a midpoint or something like that, okay, based on what your requirement is. So if we say the government will be more interested in this, right, maximization of farmers profit. In the past few years, the government has been talking about doubling farmers income and so on, so they will be more interested in this. But as an ethanol production company, or even as a consumer of ethanol, we'll be more interested in the minimization of ethanol cost, right? So based on the objectives, we need to decide what's important for us and then choose from that. So based on these objectives, they have there are some preferred districts where biorefineries can be located, right? So if you want to minimize ethanol cost, you have to locate your biorefineries in Jalna, Pune and Kolhapur. And if you want to use less irrigation water, then you have to go to Aurangabad and Satara. Similarly for water footprint and farmers profit. Okay, these are just some results. So yeah, we are at the end of the lectures. We'll just go in for the questions for this week. All right. So the first question is, vehicle exhaust, that is the tank to wheel emissions, account for about 2/3 of the life cycle greenhouse gas emission, right, of fossil fuel vehicles, as you've seen in that pie chart in the recap slide, if you remember. So if you replace them with biofuels, how will it aid in enhancing environmental sustainability? So that's the question, and your options are: A, biofuels emit lower CO2 than fossil fuels during combustion to produce the same amount of energy, or B, the carbon dioxide emitted to manufacture biofuel compliant vehicles is lower than that of conventional fossil fuel vehicles. C, the carbon dioxide emitted from biofuel vehicles is carbon neutral, like, because we are not adding any new CO2 to the atmosphere. Or D, all of the above. I hope the question is clear to you. I'll just read it out again. Vehicle exhaust accounts for about 2/3 of the GHG emissions of fossil fuel vehicles. So if you are replacing it with biofuels, how will it enhance environmental sustainability? A, does it emit lower CO2 than fossil fuel vehicles itself, or because it emits lower, the manufacture of biofuel vehicles emits lower carbon dioxide, or C, the CO2 emitted from biofuel vehicles is considered carbon neutral, or D, all of the above. Okay. Second question is, which of the following statements are true? A, levelized cost levelized cost is an equalized cash flow for equal time periods. Okay. B, money receivable a year later is worth more than the same amount of money at hand today. So let's say you have 100 rupees at hand today, but and you have 100 rupees receivable 1 year later, which is worth more. So that's what this option is. C, the unit cost of an equipment will be usually higher for higher capacities. Or D, both B and C. Third question is, which of the following statements are true? Methane and nitrous oxides are more potent greenhouse gases than carbon dioxide. B, NOx emissions and ammonia emissions cause acidification of soil and water bodies. C, excess nutrient runoff causes eutrophication of water bodies. Or D, all of the above. Alright. The next question is, which of the following are techno-economic indicators? A, you have the annual yield of biofuels from a plant, like tons per year, the annual yield of biofuel. B, annual availability of feedstock for biofuel production. C, levelized cost of biofuel. Or D, all of the above. Question 5 is, which among the below pairs of indicators are not conflicting objectives? So there is a little bit of logic involved here. A, biofuel cost versus farmers' income. Okay, we have seen this just a few slides before. Plant capacity versus transportation cost. Okay, so I've explained this as well. You have to think about the economy of scale and then the transportation cost, right? C is plant efficiency versus biofuel cost. Or D, you have the feedstock availability for first generation ethanol production versus the food grain availability for hunger eradication. So which of these are not conflicting objectives? Next is, which of the following statements are true? A, the mean ratio of the mass of small particle samples to its volume is called particle density. Okay, I have not told you what particle density is. You have, let's say rice straw pellets. All right, so you take one pellet from that, you measure the mass of that, you measure the dimensions of that, calculate the volume, okay, and then mass upon volume is the density. So that is particle density. Okay, so you take one particle or one unit of that and measure that, so that is particle density. Okay, so now we are clear, I think. Okay, so your option B is the ratio of the mass of a large quantity to the volume of this quantity, volume that this quantity occupies is called bulk density. So you take a huge amount of certain solid or certain biomass or something, and then dump it in a container. You measure the you have the mass, you know the volume, so mass upon volume, that is the bulk density. That's what this means. C is the higher void space between particles lowers the bulk density. So when you have a lot of particles like rice straw pellets or something, or even sand, let's say you're taking a lot of sand and then you're dumping it in a huge container, the particle will have certain volume, right? Okay, it will occupy a certain volume inside that container, but there will be interparticle distance. Okay, there will be a space in between that is not occupied by any, it will be air basically, right? So if there is that air, if more air is present between the particles, then that means that there is more void space. Okay, that reduces the bulk density. Okay, so that's what this means. The higher void space between particles lowers the bulk density, or D, all of the above. Okay, so small numerical here. So it is reported in literature that a gas turbine system with heat recovery steam generator with an output capacity of 26.3 megawatt, the cost is given 18.9 million in 2001. Then the scaling factor for this component is given. Okay, so you need to find out the unit cost of the same system for an output of 100 megawatt. Okay, the formula is given, the scaling formula. You have so essentially what you have to do is, you have been given C1. C1 is yeah, this is the cost. So C1 is this. You need to find out C2. Sorry. V1 is given, V2 is given, alpha is given. All you have to do is apply it and find out what is the cost for 100 megawatt, for the system of 100 megawatt, and then divide it by this. So you need the unit cost, right? So divide it by this and you'll get the answer. So I'll be discussing the answers during the next week. All right. The next one is, okay, this is a straightforward numerical. You need to calculate the 100-year global warming potential for a process given that the overall CO2, methane and nitrous oxide emissions are so and so, right? 6, 11, 8, 11 grams, 8 grams. So the warming potentials of methane and nitrous oxides, nitrous oxide are 25 and 298 times that of carbon dioxide. That means that whatever value you have here, you have to multiply this by 25, multiply this by 298, and then add it to this and then find the value. But please note the units here. This is in kg, these two are in grams, so you need to do the unit conversion. Okay. The next is the bulk density of round rice straw bale. You would have seen rice straw bales, right? The cylindrical rice straw bales. That is about 90 kilogram per meter cube. So when you pelletize it, that is after densification, the density increases to 700. Okay. And if all other parameters are equal, so I want you to calculate the ratio of the transportation cost of 1 kg of rice straw bales and pellets for equal distances in vehicles of equal volumetric capacity. Okay, let me explain this. So you have a vehicle, okay, with some volume, right? A truck, let's say. So you are carrying, first you are carrying these rice straw bales, then you are carrying rice straw pellets. Okay. So what is to carry 1 kg of each, how much is the cost? Okay, everything else is the same. Okay, that's why. So what you have to do is, you are given the formula here. So this TC is the weight capacity of the vehicle. All right. Everything here you don't have to worry about any of this, because all of this is a constant. All of these are constants. So you just put some x. So x divided by TC. So TC is the weight capacity of the vehicle. All right. So now you know the bulk densities. So what is the formula for density? Density equals mass upon volume. Okay. So you know that mass. So from that you can get mass equals density into volume. Right. Now you are given that. So this is, since this is the weight capacity of the vehicle. So density, that is the bulk density, multiplied by the volumetric capacity of the vehicle. So you have some x divided by density into volumetric capacity of the vehicle. So since it is given that they are equal volumetric capacity, that volumetric capacity is also a constant. So you can substitute it with some y. So all you will get is some y divided by the density, the bulk density. That's it. So you want C1 upon C2. So you will get it is inversely proportional to that. You will get rho 2 upon rho 1. That is the, if you're taking C1 to be the straw bale and C2 to be the pellets, then you'll get the inverse of that. So you just need to do a ratio of the bulk density to the bulk density of the pellets to the bales. That's it, and you'll get the answer. So now we have already come to the end of this. So if you want, you can just take a screenshot of this. So this is a small activity that you can do at home. All right. So complete combustion of biomass. So biomass, this is not the this is not a standard formula or something. It depends on the elemental composition. So this is something that we calculated in our lab using, we did the elemental composition and we arrived at this chemical formula using that elemental composition for a certain biomass. Okay, so when it reacts with air or oxygen, that is when it is burning, right, it creates water vapor and carbon dioxide. So the question here is, how many moles of oxygen will completely combust 1 mole of biomass? Okay. So with that, you can also find out by combusting 1 mole of biomass how much carbon dioxide can be is produced, right? I'll give you a hint here. You just have to balance this equation. Okay, how can you do that? You have 3 unknowns. Okay, you have to find x, a and b. Okay, so you need 3 linear equations and you will get that very easily. I'll give you one example. I'll give you one answer myself. So you look at the carbon balance. So there is 1 carbon atom on the left hand side, that is the reactant side. How many carbon atoms are in the product side? You have b carbon atoms. So b equals 1. So that's it. So b equals 1. So similarly, you balance hydrogen and oxygen. So you will get x and a. Alright, and that's it. And the second part of this is calculate the molecular weight of this biomass when it is the atomic weights are given. Carbon is 12, hydrogen is 1, and oxygen is 60. So it is a very straightforward. You just have to multiply and add, and you will get the atomic weight. Molecular weight of this biomass. Okay, so that's it. You can just take a screenshot or you can download it. I think the Google Sheet is already shared with you, right? So you can download it and then you can do this on your own. All right. Okay. So we are at the end of this lecture. Okay. So thank you so much for listening with patience, and yeah. Thank you. So I'll see you all next week, same time around 6 o'clock, and have a great weekend. Thanks.